Chalo guys, hey everybody, we're live and in stereo. So today we'll start off with the next topic, which is ionization energy. We're done with electronic configuration, but there were two questions that a student asked me in my WhatsApp DMs, and those two questions were so beautiful that I wanted to share it with you guys. And the thing is, if you want to ask me questions, please ask it in the group chat so that everybody else can also benefit from it rather than DMing me, because I barely see the message. I have like 700-800 messages on WhatsApp pending. So I barely see the messages. Always discuss in the group because I open all the groups from time to time. But the student asked me, said, when you were teaching shorthand electronic configuration, just a couple of things before we start ionization energy, right? So when I was teaching shorthand electronic configuration, you said that it actually helps us determine the outermost electrons as well, right? So if I talk about the shorthand electronic configuration of rubidium, and it helps us determine the group that it's going to be in, right? So if I talk about the shorthand electronic configuration of rubidium, what is that, guys? Can you guys tell me that from the periodic table? Can you guys tell me that good stuff? Wait, let's add the periodic table here, and okay, that's O level periodic table. But it doesn't really matter, to be honest. O levels, because we are not concerned with the numbers here. So that's 1, that's 2s, that's 3, that's 4, that's 5, and here your P starts from 2, so that's the P block, 2, 3, 4, and that's the D block, 3, 4, because D starts from 3, right? So if I want to talk about the shorthand electronic configuration of rubidium, it's what? Krypton 5s1, right? So it's krypton Kr 5s1. And so this tells me the outermost electron is basically in the s orbital, and the outermost electron is only one. You only have one outermost electron, because see, the principal quantum number, which is the fifth principal quantum number, that's the outermost principal quantum number, and that only has one electron. Therefore it's in group 1, right? Makes sense. That's why it's in group 1. Like if you look at beryllium, if I talk about the shorthand electronic configuration of beryllium, it's what? Beryllium is helium, and then if I want to write this, it's going to be 2s2, so 1s2, 2s2, but I'm going to write the shorthand electronic configuration. It's helium 2s2. Sure. So helium 2s2. Now I'm going to say, hey, the outermost electrons are 2. The outermost electrons for beryllium are how many? There are 2. So can I say that beryllium is in which group? The beryllium is in group 2 because it has 2 electrons in its outermost shell. Now if I want to talk about nitrogen, let's suppose, nitrogen's shorthand electronic configuration is helium 2s2, 2p3. So if you check out the outermost electrons, that is defined by the principal quantum number. So how many electrons do you have in principal quantum number 2? That's 2 plus 3, 5. And that's why you have nitrogen in group 5, because it has 5 electrons in its outermost shell. And that is the beautiful thing about your shorthand electronic configuration. It also tells you the group number of that particular element, because you are writing the electronic configuration in such a way where you're only representing the outermost electrons, which in this case is 1, in this case is 2, in this case is 5, in nitrogen's case, right? But the student asked me such a beautiful question. Why would that's not a part of our course right now. You don't have the duplet rule and this, that. We'll learn more of that in chemical bonding. Forget about that for now. Okay, so the student asked me, said, if I were to write the electronic configuration, let's suppose of vanadium, what is that? Or maybe of nickel. Let's suppose I want you guys to write the shorthand electronic configuration of nickel. That's what? Argon, and then it's 4s2 and 3d, 1 2 3 4 5 6 7 8. So argon 3d8 4s2. Sir, does that mean that your nickel is in group 2? Because see, the outermost electron for transition elements, I'm not going to talk about transition elements, I just want you guys to have the understanding, the basic understanding of your O levels, which was that the D block elements, not all, but transition elements are found in the D block. This is the D block. Now the problem with the D block is that even if I write the shorthand electronic configuration, you guys might think, hey, the shorthand electronic configuration is giving me 2 electrons in the outermost shell. The D is not the outermost shell, the 4s is now the outermost shell. Remember when I told you if you fill out the 4s, it becomes the outermost, right? So the 4s is the outermost shell. So does that mean that transition elements are in group 2? No, they aren't. They're in the D block. So that's an exception. That's an exception. So remember, the shorthand electronic configuration, which tells you the group, only applies to all the other groups, not the D block. So in the D block, all the electrons are in the 4s. The outermost electrons are in the 4s orbital, right? They're in the 4s. They're not in 3D, they are in the 4s, right? So that's the exception to the shorthand electronic configuration, telling you guys the groups, right? So always remember that all these transistors, so even if I talk about chromium, even if I talk about chromium, or even if I talk about manganese is what? 3D, 1, 2, 3, 4, 5. So 3D 5, 4s2. The outermost electrons are in the 4s right here, not in the 3D. Because realize that the outermost electrons are determined by the principal quantum number. So the higher the principal quantum number, that's the outermost electrons for you. So between 3 and 4, where are the outermost electrons? In the 4. In principal quantum number 4. So remember guys, this is an exception. Shorthand electronic configuration does tell you the group number, but not for the D block. Because all D blocks, most of them have their electrons in the 4s, or maybe in the in the 5s or whatnot. In our course, it's just going to be till here, till zinc probably, the D blocks. You won't go to erythrum and zirconium and whatnot. So in this case, the outermost electrons are where? In the 4s, right? So this is an exception. This doesn't tell me the group number. All the others would, but this wouldn't, right? So in D blocks, you don't know that stuff. In D block, you can't, actually figure out the group number from the what's it called? From the shorthand electronic configuration, right? Makes sense, guys? Okay. And the next thing I told you guys about was what was the other thing that I wanted to discuss? The other question that the student asked me was about orbit and orbitals. Remember, orbit basically refers to principal quantum number or principal quantum shell. Orbitals are something totally different. Orbitals are basically regions in space where there's a high probability of finding an electron, and it can only hold a max of 2 electrons. Orbit is basically a fancy way of saying principal quantum number, principal quantum shell, shells, energy levels, and whatnot, right? That's just the other name. And the student said, what are the differences between the two? That's the biggest difference. Orbit corroborates to principal quantum number. Orbitals are just the regions in space in which there's a high probability of finding an electron, which is almost 95%. And if I show you guys the differences between the two, that's the last thing I'll do, and then we'll go on to our ionization energy. So these are a couple of differences. You'll never be asked these differences, but if you really want to know, you can have this. What is an orbit? A well-defined circular orbit followed by an electron evolving another way, and this is a region in space where the electron is likely to be located. But we know we need to define it like something else. We need to define it as region in space where there's a high probability of finding an electron, almost 95%, and it only holds a maximum of 2 electrons, right? It represents a planar motion. It represents 3. So when we talk about orbits, we usually show orbits with circles. The orbits that we've been showing, the shells that we've been showing since O levels and IGCSE, which we now don't do. In in AS level, we don't do that. We show electron inbox diagrams. So this represents a planar motion, but orbitals are 3-dimensional. It represents 3-dimensional motion. What this means is you're showing the px, the py, the pz, and even the s orbital is in all the planes. So that's what we do with orbitals. And orbits are non-directional and hence cannot account for the shapes. Orbitals have different shapes. Yes, see, in orbits we used to just make circles. In our O levels and IGCSE we just used to make circles, but in orbitals we now know the reality of things. We know that you have the s orbital, which looks something like this, the p orbital, which looks something like this, and then you have the d orbitals, but we don't look into the d orbitals in our AS level, right? And then the maximum number of electrons can be 2n squared. Remember, if you want to calculate how many electrons are there in principal quantum number 4 or orbit 4, what do? 2 4 square. 2 times 4 ka square. What does that give me? 4 square 16. 16 times 2, that's 32. That's how we roll, remember? So that basically the orbit, the term orbit corroborates with principal quantum number. It's the same thing. And for orbital, it can't accommodate more than 2 electrons, and the electron is viewed as a localized particle. As a localized particle means when we used to make electrons in O levels and IGCSE, we used to show them in these shells, remember? And when we used to do that, it gave off the the impression that the electrons are basically localized, which means they will follow this circular path. But that's not true. The electrons don't follow a circular path. That's the problem with showing electrons in orbits, because if I show it in orbits, it basically gives off the idea that the electrons are basically localized or they are following this circular path. But that's not true, because the electrons are basically, there's a probability of finding them in the orbital. So these are differences. These I took from the IB book, but nobody cares. It's never going to be tested in your course. But if you wanted to know, you could know. Yes, it's being recorded, Zumar. But now let's move on to our, let's come back to our course content, which is what? Which is ionization energy. Now, what in the hell is ionization energy? Sorry guys for being so sassy. Yeah, I just can't with myself. I'm just so crazy. I sometimes think to myself, yeah, kya pagal hu main? I'm like the Mad Hatter. Have you guys watched Alice in the Wonderland? I'm like that Mad Hatter from Alice in the Wonderland. I swear. I sometimes think to myself, like, damn, sir. Okay, so ionization energy. What in the hell is ionization energy? Remember that when I told you that Erwin Schrödinger plucked electrons and proved the idea of subshells and orbitals, and he proved Bohr wrong? Remember that? He used to pluck those electrons and he came up with the idea of subshells, the S subshell, the P subshell, the D subshell, and whatnot and whatnot. Yes, remember that? Well, that plucking of electrons, or removing of electrons is called ionization energy. That's it. That's the energy associated with removing electrons. How much energy would be required to remove electrons, right? And what he did was, how in the world did he do that? Well, he took a sodium atom, a solid sodium atom, and he provided it with heat. He provided it with heat, and he realized that the solid was actually melted. The intermolecular forces of attraction, which you studied in O levels, remember the change of state? So the intermolecular force of attraction were overcome, and the solid sodium was actually melted into sodium liquid, right? And the problem with that is that the electron was still not removed. It wasn't removed, So what he did was he provided it with more heat. He took liquid sodium and he provided it with more heat, and he realized that instead of removing the electrons, he actually vaporized sodium. Which means he converted sodium liquid, which was in the molten state, to sodium gas. The electron was not removed. That was the biggest problem. Electron wasn't removed. Electron wasn't removed even here. It wasn't. That was the biggest problem. But then he realized that now let me heat this sodium vapor more and more, and that is when the electron was removed. So he took sodium vapor, sodium gas, he heated it so much that the electrons were removed, and you ended up with sodium 1 plus, right? And that was also in the gaseous state. Obviously, if you remove electrons from vapor, you'll have ions, but I'll still be in the gaseous state. So this is when he realized that I could remove electrons. So he couldn't remove electrons from solid sodium. He actually melted it. He couldn't remove electrons from liquid sodium. When he heated it and provided it with energy, he actually vaporized it. But he realized that once it was vapor, sodium gas, only then was he able to remove electrons. Which means that electrons are usually removed when all the gluing forces like intermolecular forces of attraction, all the gluing forces, they are overcome. Even metallic bonding, sodium solid has metallic bonding in it. So you realize that electrons are only removed after all the other forces are overcome, and then is the It's the time for the electron to be removed, right? So that was the conclusion that he made, that in general, electron can only be knocked off if all the bonds, the metallic bonds, the intermolecular force of attraction have been overcome, which means that electrons can only be removed from a particular atom if it's in its gaseous state, right? So you can write it like this, or you could also say that sodium gas in its gaseous state, there was a removal of an electron. We don't write symbols for electron, sorry. And then you have sodium ion forming, right? So you could write it either like this: sodium gaseous state, electrons were removed, give you sodium ion in the gaseous state, and sodium gaseous state, electron was removed, because we know we write loss of electrons on the right hand side. And it's just mathematics. There's no charge here, but now this is 1 plus. And if you want to balance an equation, the charges on the left hand side must be equal to the charges on the right hand side, right? So if you want to balance this out, you'll realize that on the left hand side you have 0 charge, on the right hand side you have plus 1 charge, but when you add an electron, plus 1 minus 1 gives you 0. That's why we write loss of electron or removal of electron on the right hand side in order to balance the equation. It's just mathematics. And if you want to look at this, how is this equation balanced? Because you had 0 charge here, but minus electron has a negative charge, right? So electron has a negative charge, and I'm putting minus here because I've written the minus symbol. So minus into minus, what does that give me? Plus 1. So the overall charge on the left hand side of my equation is plus 1. And what's the overall charge right here on the right hand side? That's also plus 1. That's why you can either write the equation like this, or you could write the equation like this. It's up to you. I usually prefer this because that's the convention. You guys can also go against the convention as long as the left hand side charge equals the right hand side charge, right? So that was the conclusion that he made, that if I were to remove an electron, aka I want to pluck an electron, which I call ionization energy, I can only do that if sodium is in its gaseous state. So sodium was in its gaseous state, he plucked off the electron, he gave me sodium 1 plus ions, and the electron was plucked off, right? But that's not the real reason. That's what he realized, but the real reason is not that. The real reason why sodium gas is used when we talk about ionization energy is because when sodium is in its gaseous state, or if sodium is in its solid state, let's suppose, and I want to figure out how much energy would I need to remove an electron from sodium, right? Now, if you look at the solid state, you'll realize that for sodium solid, all the sodium atoms are tightly packed. Isn't that true? All the sodium atoms are tightly packed, because that's what happens for solids. Solids particles are close together, they are tightly packed. Yes, agreed. O levels IGCSE, states of matter, chapter number 1. Everybody agrees with me that solid particles are tightly packed. Now, if I want to remove the electron, the problem is that even if somehow I was able to do that, although I can't, but if somehow I was able to remove electron from the solid, that would not give me an accurate value. Why would that not give me an accurate value? Because the solid particles are so together that this electron would be influenced by the next sodium atom here, by the nucleus of the sodium atom, or maybe by the electron of the sodium atom. So the value that you are going to get to remove this electron will not be accurate, because this electron removal, the energy that you need to provide to remove this electron, will be influenced by the other atoms which are close together to it. So by the nucleus of the other atom which is tightly packed. And same case is for liquid. Liquid particles are also close together but slightly separated. So what do? What we do is we convert this into sodium gas, because if sodium is in its gaseous state, you'll realize that the particles are far and apart. The sodium atoms would be far and apart. And now if I were to remove this electron, this removal, this energy that I'm going to use to remove this electron or to knock off this electron, will not be influenced by the other sodium particle or the sodium atom, because it's going to be far and apart. So the value that I'm going to get here is going to be very accurate relative to the value that I'm going to get here. That's why remember that whenever we talk about plucking off electrons, which is ionization energy, we talk about gaseous state, atoms in their gaseous state. Yes, so a lot of teachers, they just teach you what ionization energy is, they just make you rote learn it, but they never teach you why it's in its gaseous state. So there are two reasons. Firstly, it's, when you start to remove an electron, you first of all have to overcome all, usually you have to overcome all the gluing forces, da 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 da, and then you are able to remove off the electron, because removal of this electron requires the highest energy compared to melting it or boiling it or whatnot, right? And then, or vaporizing it. And then the real reason is also, if I want to remove electron from a solid, or if I want to remove electron from a gas, you realize that if I want to remove it from a solid, the value is not going to be accurate, because there'll be a lot of interaction from the other atoms, because they are also close together. So the value that you're going to get is not going to be that accurate. But if I were to remove it from a gaseous atom of sodium, then the value that I'm going to get, which I am calling ionization energy, the energy that I'm going to provide to pluck off the electrons, is going to be quite accurate, because there's going to be no influence of the other atoms, since they are far and apart, right? So if I were to write the ionization, the equation for removing the electron of sodium gas, I'm gonna say, hey, sodium was in its gaseous state, I plucked off an electron, and I got sodium ion in the gaseous state. Normally we put the charge on the electron, because we know electrons are negatively charged, so we put this minus on top of it, and that's just a conventional way of writing electrons in equations, right? We don't write symbols with electrons. Done. Now, when I remove the electron from sodium, what was the electronic configuration of sodium? Principal quantum number electronic configuration. 281? Yes? It was 281. Now, when I removed an electron, what happened? What is the electronic configuration now? 28. True? When I removed an electron, the electronic configuration is now 28. This is called the first ionization energy. What is the first ionization energy? The energy that I required to remove. I'm not giving you as the exact definition yet. I'm just building up concept. The energy that I had to provide to pluck off the first electron, right? And you know that electrons, if you want to pluck off electrons, how do you do that? Are electrons removed from the innermost shell, or electrons are plucked from the outermost, and then this, and then this? How are they plucked? It's common sense. The innermost electrons are not plucked first. First, what happens? The outermost, this electron, is going to be plucked first. Yes, so first the outermost electron is plucked, it's removed, and that's what I call the first ionization energy. My electronic configuration went from 281 to 28. There's one, you had 3 shells here, now you have 2 shells, right? So I removed this electron. Let's suppose I required X amount of energy, because I don't remember the figures. So let's suppose I required X amount of energy, to pluck off this electron. Sir, when we pluck off electron, do we have to provide the ionization energy? No, ionization energy, Aisha, is just a fancy way of saying plucking off electron. It's just the energy you provide to pluck off the electron. That's called ionization energy, ionization energy. And you'll get the concept after I teach you the proper definitions for it. For now, just realize that plucking off electrons is called ionization energy. Yes, absolutely, just like providing electrical energy. ऐसे ही है बिलाल, it happens like this. बिल्कुल ऐसे ही होता है. You provide it with energy and you pluck it off. Okay, and now if I want to remove another electron, from this particular gaseous ion, so I have sodium gaseous ion and I want to pluck off another electron, I can continue to do that. That's what Erwin Schrödinger realized. I could continue to do that. He plucked off another one. So now you have a charge of 2 plus, because I plucked off another electron, and that's right here. And then I can pluck off the third electron. So from the 2 plus gaseous ion, I can pluck off the third electron. And I can do that forever and ever and ever until I am able to pluck off until I pluck off all of these electrons. Now, how would the energy vary? The idea behind learning ionization energy or plucking off electrons is, how would the energy vary? What does that mean? Well, what that means is, I can remove this electron, I can remove 8 more electrons, I can remove these 2 electrons as well. How would the energy vary? Would I need to provide more and more energy as I remove electrons, or would I need to provide less and less energy as I remove electrons? Well, the first idea that you need to realize is that you are providing energy. You are providing energy. So is it endothermic or exothermic? I am providing it with energy. I am providing energy to remove this, I am providing energy to remove this, I am providing energy to remove this. So obviously it's an endothermic process. Ionization energy, all the energy associated here is what? It's endothermic. I am removing electrons by providing it with energy, right? So it's endothermic, 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 endothermic. But the problem was that when Erwin Schrödinger removed the first electron, he required X amount of energy to do so. And then he took 2,8, which is your sodium 1 plus gaseous ion. He took that and then he removed one more electron from that. So what do you have now? You have 2,7. You removed one more electron. And he realized that this was actually requiring a lot more energy. A lot more energy compared to the X amount of energy that we initially needed to provide. And now, as scientists, we need to dive deep and learn why in the hell was the second ionization energy way higher than the first ionization energy. It's just plucking off electrons. Ionization energy, for now, just think of it as plucking electrons. So why was energy for the first electron to be plucked much lower than the energy for the second electron to be plucked? And what he realized was that that the nucleus is pulling these electrons towards itself, right? The nucleus is, if this is my nucleus, let's suppose the nucleus is pulling these electrons towards itself. Now the outermost electron was pretty far from the nucleus. It was in the third principal quantum number. So let's suppose I required X amount of energy to remove this electron, which was my ionization energy. To ionize sodium, I required X amount of energy. But now, if I were to remove the electron from the second principal quantum number, would I require more energy or would I require less energy? Well, obviously, Dumbo Jumbo, it's so evident. I would require more energy because this electron right here, the electron in the second principal quantum number, is way closer to the nucleus. So if it's way closer to the nucleus, it would what's it called? What's the English term for that? It would experience a stronger pull from the nucleus. It would experience a stronger pull from the nucleus. This electron is furthest from the nucleus. So if I were to separate it from its friend, the nucleus, I would require X amount of energy. But if I were to remove this electron, this is way closer. It's like separating a kid from their parents. If a kid is, distant from the parents already, you just need to provide it less energy and they'll be removed. They'll be separated from their parents. But if a kid is very close to their parents, they will experience a stronger pull from their parents. So you need to provide it with more energy to actually pluck this electron. So what happens is that if I look at my beautiful two equations, which are the first ionization energy and the second ionization energy, if I remove the first electron, it requires X amount of energy, but there's going to be a big jump. There's this big jump, big jump from the first to the second. Why? Because the second electron is removed from a shell which is closer to the nucleus. And therefore it experiences a stronger pull. That's why to remove it, you need to provide more energy. And these big jumps that I'm talking about, these big jumps were a proof of shells. That's how we proved shells. Because we do not have these big machines and all of that good stuff to look at, or to visualize this. But these big jumps between, removing one electron and the other electron, this big jump actually was an indication of different principal quantum numbers. So this electron is being removed from principal quantum number 2, and this electron was removed from principal quantum number 3. So that's how he actually developed the idea of shells and even different energy levels. So remember this, that Erwin Schrödinger actually figured out the idea of shells with the help of ionization energy, which is what? Which is just plucking off electrons. And he realized that each successive ionization energy is endothermic. Is the concept that we learned a minute ago. Successive ionization energy is like, one after the other. So this is the first ionization energy, that's the second, and you keep on removing electron. So second to third, third to fourth, fourth to fifth, fifth to sixth, that's called successive ionization energy, removing electrons one by one, one by one. So one from here, one from here, one from here, and so on and so forth. So it's endothermic because you are the one providing it with energy. You are the one providing it with energy. And this could actually also indicate, it can also help you identify or deduce the number of electrons in the outermost shell. My question to you guys is, how do I know that sodium has one electron in the outermost shell? Now visualize this. Okay, how do I know that sodium has one electron in the outermost shell? Well, if I pluck the outermost electron off, no, it's not about group 1. That's the experiment actually placed it in group 1. But how did you know initially, Bilal, that it had one electron in its outermost shell? Now close your eyes for a moment. I'd like you guys to visualize this. Close your eyes. Now think of these 3 shells of sodium. Think about these 3 shells of sodium. Now, when Erwin Schrödinger removed the first electron, it was like, okay, I removed the first electron, that's Gucci stuff. But when he removed the second electron, it actually required a lot of energy compared to removing the first electron, which means that now the shell has shifted. There's a big jump, and that big jump could only be explained if I were to say that the outermost electron of sodium was only 1. Because if there's 1 electron in the outermost shell, you can remove that. But if you were to remove the second electron, then if there were 2 electrons in the outermost shell, then the second electron removal would not require that high of energy. But you realize that it required a lot of energy. There was a big jump between removing the first electron and the second electron. And that big jump actually proved the idea of shells and even the idea of how many electrons are there in the outermost shell, right? So if there's a big jump from the first ionization energy to the second ionization energy, that means that when you plucked the first electrons, it was Gucci, I don't care. But when you plucked the second electron, it required a lot of energy, which means that now the shells have probably shifted and the second electron is removed from a shell closer to the nucleus. Bilal, I'll cater to that in a while. From Na2 plus to Na3 plus, would this energy increase? Yes, it would increase, but it wouldn't be a big jump. So it wouldn't be a big jump. It would still increase, Bilal. So if I were to remove an electron from, sodium 1 plus to sodium 2 plus, between this and this, there'll be a big jump. But between this and this, the energy would increase, but not that much. Why? We'll learn that in a while. It's always increase. Yes, you're right, Bilal. It is the same subshell, but you don't know the idea of charges yet. So once I teach you that, then you'll figure out why there's going to be an increase here. Okay? Acha ji. Now, what in the hell is ionization energy? Sir, abhi tak you were talking of plucking an electron, but now let's talk about ionization energy scientifically. Well, it's basically the energy required. It's the energy required. In our time, we used to write the minimum energy, but now it's just the energy required to completely remove 1 mole of electrons from 1 mole of gaseous atoms or gaseous ions, or ions, gaseous ions. So from gaseous atoms or gaseous ions. What in the hell does this mean? Well, I've already explained it. It's the energy required to remove 1 mole of electrons, and that's 1. In the equation, when you don't have anything, we write 1. So it's the energy required to remove 1 mole of electrons from either gaseous atoms or gaseous ions. It's the energy required to remove 1 mole of electrons from either gaseous atoms or gaseous ions. It doesn't really matter. You could do that with ions, you could do that with atoms, and that is what ionization energy is. Why don't we talk about 1 electron? Why do we talk about 1 mole of electrons? Because you realize in laboratory, measuring 1 electron, removing 1 electron becomes very difficult. That's the entire idea of moles and stoichiometry. When we say that in 1 mole you have 6.02 into 10 is power 23 electrons, so that is the reason why we say removal of 1 mole of electrons, because you can't really just remove an electron from a single atom very, very specifically. We have to remove it from 1 mole of atoms. 1 mole of electrons would be removed from 1 mole, because that's easier for us to measure actually. So that's the idea behind 1 mole. And why is it gaseous? To isolate the atom, to isolate the ion, or to isolate the atom from the interactions with the corresponding or with the atoms closer to it. That's why we need it in the gaseous state to actually accurately figure out the energy required to pluck that electron off it. Or otherwise, if it's in its solid state or molten state and you try to remove an electron, the problem with that would be that the electron that you are removing, you wouldn't get the proper value for it, because it'll experience effects from the nucleus of the atoms which are closer towards it, and whatnot and whatnot. Yeah? That's what ionization energy is. Now, if I say write the first five, oh, okay, that's what ionization energy is in general. But in our exam, we are not required to write the definition of ionization energy. We are not required to write the definition of ionization energy because it's very general. Energy required to completely remove 1 mole of electrons from 1 mole of gaseous atoms or 1 mole of gaseous ions. That doesn't really matter for us. It's very generic. We just need to know how to define first ionization energy, and that you need to know. And this is what the examiner is going to ask you in the exam. Now, how do you define the first ionization energy? Well, if you look at the equation, if I were to write the first ionization energy, what is that? I take sodium gaseous atom and I remove 1 mole of electrons from it, and I get 1 mole of sodium gaseous ions. Yeah, 1 mole of sodium gaseous atoms, I get 1 mole of sodium gaseous ions, and I remove 1 mole of electrons from it, right? So if I were to write the definition for it, it's the same as the equation. What is it? It's the energy required. In our time, it was the minimum energy required, but now they've realized that students know it's the minimum energy required, right? So it's the energy required to remove 1 mole of electrons. So to remove 1 mole of electrons from, where do you remove it from? From 1 mole of gaseous atoms or from 1 mole of gaseous ions? Remember, ionization energy, you can remove it from 1 mole of gaseous atoms or from 1 mole of gaseous ions. But I'm talking about the first ionization energy. In the first ionization energy, do you have 1 mole of gaseous atoms or do you have 1 mole of gaseous ions? Is this an atom or is this an ion? Sodium gas. So to remove 1 mole of electrons from 1 mole of gaseous atoms. Yes, you guys are right. From 1 mole of gaseous atoms. And what does that give me? What does that give me? If I remove 1 mole of electrons from 1 mole of gaseous atoms, if it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, what does that give me? What does that give me? To give 1 mole of, absolutely. So to give 1 mole of gaseous ions, or to form 1 mole of gaseous ions. That's it. Gaseous ions and positive, So to become 1 mole of positive ions. Positive gaseous ions. Yeah. So to give you 1 mole of positive ions, it's giving me 1 mole of positive gaseous ions. Yeah. And you remove the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of that element, or of that element, doesn't really matter. But that's how you need to define it in the exam. That's how you need to do it. So if I were to write the first ionization energy for element X, how would I do that? If I were to ask you guys to write the first ionization energy of element X, how would I do that? Well, I do that by saying that first of all, S must be in the gaseous state to isolate it, so that the ionization energy we get, the energy value that we get, is pretty accurate. So to standardize measurements and relate to real world quantities, I need to get it in the gaseous state. And then what do? I need to remove 1 mole of electrons from it, and I would get 1 mole of gaseous ions. Why 1 mole of electrons? Because it's not the examiner is never going to ask you why gaseous state, why 1 mole of electrons. I'm just telling you guys this to solidify concepts, because no teacher is going to tell you why they do it. Why 1 mole? Why 1 mole? To standardize measurements and relate to real world quantities, because in real world we deal with moles. We deal with a single atom or a single ion or a single electron. So if ever the examiner asks you why 1 mole, which he's never going to do, you can literally say to standardize measurements, which relate to real world quantities, you know. But they're never gonna. Why gaseous atom? Because we wanna isolate the atom to get an accurate value, of ionization energy. Yeah, because if it's not gaseous state, then you will realize that all the other atoms would be interacting with it, and the value that you might get may not be that accurate. So that's the first ionization energy. Can you guys write the first ionization energy equation for Y? For element Y. Yes. So it's what? First of all, always think it's Y gas, then you get Y1 plus gas, and then you have 1 electron, 1 mole of electron to be removed. So if I were to define ionization energy, it's just reversing the equation. So it's what? The energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to give me 1 mole of positive gaseous ions. To give me 1 mole of gaseous positive ions or positive gaseous ions, it doesn't really matter. That's it. Can you guys write the first ionization energy of sodium? That's the electronic configuration for it. Actually, don't write the first ionization energy. Can you guys write the first 5 ionization energy equations for sodium? The first 5 ionization energy equations for sodium. Yeah? Can you guys do that? The first 5. So I'll also help you guys. Remember, always write the state symbol. It's gas, sodium in the gaseous state. And then I remove. So what is ionization energy? It's removing the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to give me 1 mole of gaseous positive ions. Great. What's the second? Okay, the examiner is never going to ask you second ionization. Always write the state symbols. Only not with the electrons, but you have to write it with this as well as this. Now, what if the examiner asks you to define the second ionization energy? How would you define it though? How would you define second ionization energy? He's never going to ask you because that's not in your course, but how would you define it? Is the energy required to remove 1 mole of electrons from 1 mole of gaseous positive 1 ions to give you 1 mole of 2 plus ions, to give you 1 mole of gaseous 2 plus ions. Yes, you are right. Hydrogen only has 1 electron. It can't have second ionization energy. True. I agree. I've never said anything about hydrogen. I'm just talking about sodium. Can you guys write the first 5 ionization energy for sodium? And then, so this is the first where I remove the first electron. This is the second where I remove the second electron. This is the third where I remove the third electron. So if the examiner were to ask you to define the third ionization energy, which he will never do, but you're my student, so you must be able to deduce it on your own. It's what? It's the energy required to remove 1 mole of electrons from a 2 plus gaseous positive ion to give you a 3 plus gaseous positive ion. That's it. If I were to ask you to define the fourth ionization energy for me, how do you define it? In your exam, you'll just be asked to define the first ionization energy, which is what? The energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to give you 1 mole of positive gaseous ions. Yes. So the fourth ionization energy is removing 4th electron. And then the 5th. And then the 6th. And then the 7th. And then the 8th. Easy peasy. That's literally it. That's literally ionization energy for you. Make sense? Asan, mushkil. Now, I need to understand a couple of things here. First of all, the most common mistakes that students do. If I ask you to write the sixth ionization energy of sodium, and these things are asked so many times in the exam and students blunder here. Why? Because if I asked you to write the sixth ionization energy, what is, try to define the sixth ionization energy for yourself. How would you get the sixth ionization energy? Well, it's the removal of the sixth electron. And from what do you remove the sixth electron? What should it already be for you to be able to remove the sixth electron? What should the charge already be to remove the sixth electron? Always think like this. Okay, I have to remove the sixth electron, so if I were to write the sixth ionization, it can't be like this, so sodium and going into sodium 6 plus. No, that's wrong, because I'll have to have removed more and more electrons. Yes, you guys are right. So if I were to remove the sixth electron, sodium should already have a charge of 5 plus. You must also already have removed 5 electrons. So if I were to remove the sixth one, what am I going to do? I'll take the fifth, I'll take the sodium ion with 5 plus charge, and I'll remove the sixth electron right here, and now it'll have the 6 plus charge. You know what students do? And this is the most common mistake. Students say the sixth ionization of energy of sodium is this. Is this right or is this wrong? Which of these is right? Is this the sixth ionization energy, A, or is B the sixth ionization energy? It always confuses students, and you all are right. You guys are geniuses. It's not B, it's A, because sixth means removal of the sixth electron, not removal of the seventh electron, right? If I were to define the sixth ionization energy, it's the energy required to remove 1 mole of electrons from a positive 5, from a 5 plus gaseous ion to form 1 mole of 6 plus gaseous ions. So it's the energy required to remove 1 mole of electrons from 1 mole of 5 plus gaseous ions to give you 1 mole of 6 plus gaseous ions. Remember this. So B is wrong and A is right. So whenever you want to write maybe the 7th ionization energy for sodium, or maybe like the 8th ionization energy for sodium, that means you must be forming an 8 plus ion. That's the 8 ionization energy. And from what do you form the 8 plus ion? Well, you form the 8 plus ion from the 7 plus gaseous ion. Yeah. So always think about it like this. If I say write the 50th ionization energy for element Y, let's suppose there's an element, write the 50th ionization energy for it. Well, for me to remove the 50th electron, Y should already be 49 plus. And then I'll be able to remove the 50th electron and obviously get a charge of 50 plus. But always remember that it's in the gaseous state. It's in the gaseous state. Never forget that. Make sense? Easy peasy lemon squeezy? Asaan hai ki mushkil? Easy or difficult? Now, I want you guys to understand a couple of things. First of all, I want you guys to write the ionization energy, all the 11 ionization energy of sodium. Because realize, if sodium has 11 electrons, you can pluck all the electrons, all the 11 electrons actually. So I want you guys to write the 11 ionization energy of sodium. And I want you guys to define the first ionization energy, please. So define the first ionization energy and write the 11 ionization energy for sodium. Please do that. What are we doing? We're actually learning how Erwin Schrödinger figured out principal quantum numbers and subshells and all of that good stuff. So I'll pause the recording now, and I want you guys to write the ionization energies and define the first one, please. It's very easy to define it. You could literally write the equation first and then define it from the equation, the minimum energy or the energy required. Don't write minimum because now it's not written in your exams, but nobody cares. No, not the 11th, Bilal. I want for you to write all the 11, so from first to second to third to fourth to fifth to sixth. Yes, I want you guys to do that, because through this one example, I will explain the entire concept of ionization energy. Now I'll be writing it with you, so you guys have gotten the idea, So if I were to write the first one, always remember to write the states, always, for sodium and sodium 1 plus. So how do we define the first ionization energy? It's the minimum and it's the energy. Why am I saying minimum? Remember, in my time we used to define it like this, the minimum, so it's still stuck. It's like a tick on my tongue. So it's the energy required to remove 1 mole of electrons. Always start from right to left. To remove 1 mole of electrons from what? From 1 mole of gaseous atoms, to give 1 mole of positive ions. To give 1 mole of gaseous positive ions or to give 1 mole of positive ions, both are correct. And then if I were to write the second ionization energy, so second is what? If I were to remove the second electron, I would have to remove it from the first, from the 1 plus charged ion. So if I were to remove the second electron, I need a 1 plus charged ion. So I take this right here. Remember, always write the state symbols, which is gas, gas, and that is the removal of the second electron. How do I define it? Well, it is the minimum, it's the energy required to remove 1 mole of electrons from 1 mole of positive ions to give you 1 mole of 2 plus ions, from 1 mole of gaseous ions, gaseous 1 plus ions, whatever, right? And then the third one, so if I see, I made a mistake. So if I were to write the third ionization energy, I need to remove the third electron from a 2 plus ion. Always write the state symbols. That's 1 electron. And now I'll just quickly go over it, right? So now I'm going to speed up. I'm going to speed up because I need to write all the 11. I'm going to pause the recording and write all the 11, yeah? And then I'll play the recording. Oh, this. Play the recording. So now I've started the recording again. Obviously, always remember to write the states. Gas, 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 gas. I've written the first 11 ionization energies for you. Why have I written that? Because I want to explain a couple of concepts through this. And that'll be, the entire conceptual idea of ionization energy. And then, inshallah, in the next class, we'll complete ionization energy. Not today, because we went into a lot of depth today. Okay. Is it okay to not write 1 with an electron? Yeah, it's okay. You can just write E. You don't need to write 1 here. I'm just writing 1 to show you that it's, removal of 1 mole of electrons from 1 mole, from 1 mole, from 1 mole. It's okay not to write 1 with anything. If you want, you could write 1 with everything. And if you want, if nothing is written, that means 1, Okay, great. Now, can we be asked to write the whole ionization energy in one equation? No, Sidra. Ionization energy, if you're saying, hey, go from this to this in one equation, no, you need 11 equations, because ionization energy defined as the removal of 1 mole of electrons from 1 mole of gaseous atoms or 1 mole of gaseous ions to, to form 1 mole of gaseous positive ions or 1 mole of, yeah. So that's basically that. But the first ionization energy is defined as the removal of 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of positive ions. Awesome work, guys. Awesome work. You all have gotten the idea. Now. What was sodium's electronic configuration? It was 281, right? 281 to start with. What is the electronic configuration here? It's 28. What's the electronic configuration of the sodium 1 plus ion? What's the electronic configuration of sodium 2 plus? It's 27, it's 26, 25, 24, 23, 22, 21, then it's 2, then it's, removal of, did we miss something? 2, then you remove this electron. Is it 2 here? 9 plus. Yes, it's 2 here. Then it's 1 here, and then it's 0, right? You removed all the 11 electrons. That's the electronic configurations for the 1 plus, the 2 plus, the 3 plus, the 4 plus, the 5 plus, the 6 plus, the 7 plus, yeah? Now we have to understand how Erwin Schrödinger actually developed the idea of principal quantum numbers, or shells, Realize that you had 3 shells initially for sodium gaseous atom. 3 shells, right? Shell number 1, principal quantum shell number 1, principal quantum shell number 2, principal quantum shell number 3. Now, when you had this, this configuration right here, 281, and you removed the first electron, that was all good stuff. I removed this electron right here. It was all good. Yes, Manur, yes. We're just theoretically looking at things. Theoretically, we're looking at things. So you could remove all the electrons. It'll require a very high energy, a very, very large amounts of energy, because for sodium to be sodium, it just needs to have 11 protons. Remember, electrons are not the identity card, Manur, protons are. Okay? Now, so if I have sodium right here, and I remove 1 electron from it, that's good stuff. I removed an electron from it. X, great. But now, if I remove the second electron, which would be my second ionization energy, second electron, think about it. First doesn't really matter. Whatever energy was required doesn't really make a difference, because just looking at the first ionization energy tells you jack shit. It doesn't tell me anything about shells. But now if I remove the second electron right here, would there be a big jump or no? Would there be a big jump or no? Obviously, there's going to be a big jump. And how did Erwin Schrödinger define, how did Erwin Schrödinger explain that big jump? Well, he explained that big jump by using the idea that there must be two different principal quantum numbers. There must be two different shells. So why is there a big jump between the first ionization and the second ionization energy? Because the second electron right here must be removed from a shell which is closer to the nucleus compared to this stuff right here. So how do I explain this big jump? That the second electron is removed from a shell closer to the nucleus. Closer to the nucleus. That's why it's a very, very big jump. But now if I look at, removing the third electron. Now the third electron that I'm going to be removing, the first was from here. Alone it doesn't tell me anything. But by comparing it with the second one, I realize that, oh, there's a big jump, which means that the second electron must be removed from a shell closer to the nucleus, and therefore it would have experienced a tighter pull. That's why you required a very, very high energy to remove this compared to this stuff right here. So if you were to remove the first electron or the first two electron, the first electron for sodium, or maybe in magnesium's case where you have two electrons in the outermost shell, if you remove the first two electrons for magnesium, it's not going to tell you jack shit about the principal quantum number. But when you remove the third electron for magnesium, you'll realize that, hey, the third electron is removed from a shell closer to the nucleus, and therefore magnesium must have two electrons in its outermost shell, because the third electron requires a very, very high energy to be removed, which means now the shells have shifted, the shells have changed. Always think like this, yeah? Now let's come back to sodium. So for sodium, I removed the first one, didn't tell me anything, but when I compared it to the second one, there was a big jump. And that jump indicated that the second electron is removed from a shell closer to the nucleus compared to the first electron, right? So the first electron, the outermost shell only had one electron. And in magnesium case, the outermost shell had two electrons, because when I removed the third one, I realized that, hey, the third is being removed from a shell closer to the nucleus. So the outermost must have only had two. So it can also tell you the outermost electrons, this ionization energy. Now the question is, sir, what if I remove the third electron for sodium, which is right here? The third electron for sodium is here in this principal quantum number. Now realize, if this required X amount of energy, this would require a way, 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 way higher energy, a way higher energy. But the difference between these two right here, not the first and the third, but these two right here, would it be high? Would it be the same? What would it be? Now some of you guys may think that, sir, we'll come to p orbital later on, Mahanur. We'll talk about all the exceptions. Don't worry, huh? Now, the question that remains here is that what's the difference between these two? They are in the same shell, aren't they? They are in the same shell. And we realize that they are in the same shell. This is also in principal quantum number 2. That's also in principal quantum number 2. So what should be the difference in their ionization energy? Some of you might think, sir, this should be the same. Some of you guys might think that this should be the same, and rightfully so. This comes in your brain, hey, the first, okay, I realize that the first and the second, there's a big jump because the second electron right here is being removed from a shell closer to the nucleus. That's true. So that's why there's a big jump. But what about the second ionization energy and the third ionization energy? What about that? Well, you might think it's same, but it's not. The third ionization energy is slightly higher, and the fourth would be slightly higher than the third, and the fifth would be slightly higher than the fourth, and the sixth would be slightly higher than the fifth. And why is that the case? Why? Because now the idea of charges come into play. Remember, each successive ionization energy, so from second to third, third to fourth, fourth to fifth, fifth to sixth, sixth to seventh, each successive ionization energy is slightly higher than successive ionization energy. Each successive ionization energy is slightly higher, than the one before. Why? Because now we'll have to look into charges, the idea of charges. What happens is, see, if I remove an electron from sodium 1+, that would give me sodium 2+, and the loss of electron and write on the right hand side. You could have also written minus electron. That is your choice. And if I were to remove the third electron from sodium, I would get a 3 plus ion. When you remove 3 electrons, you get a 3 plus ion. Now realize that why would this be slightly higher than this? Also, let's write gas. I want you guys to visualize something. I want you guys to visualize. See, what happens is that each successive electron, listen to me very carefully. Each successive electron is being removed from a more positively charged ion. Each successive electron is removed from a more positively charged ion. And what do we mean by a more positively charged ion? Why would this increase the ionization energy? Well, the more positively charged ion would increase the ionization energy because the higher the charge, the more strongly it'll hold on to the remaining electrons. The more strongly, because positive attracts negative. So you will want to remove the electron, but this 2 plus charge is going to hold on to those electrons. That's what I mean when I say that each successive electron is being removed from a more positively charged ion. Which means, and this more positively charged ion will hold on to the remaining electrons. On to the remaining electrons. More tightly. Stronger hold on the remaining electrons, or more tightly electrons. And there's also another idea that you could use here, that see, you have 11 protons, but here these 11 protons just need to attract 10 electrons, and here 11 protons just need to pull 9 electrons. Now you guys tell me, the fewer the electrons, see, you have 11 protons, so 11 plus, and in one place they're pulling 10 people towards themselves, and in the other place they're pulling 9 people towards themselves. So you realize that fewer electrons also need to be pulled by the nucleus. And if fewer electrons are to be pulled by the nucleus, the pull is gonna be stronger now. It's like a tug of war. You could think of it like tug of war. In one side you're pulling 10 people, 11 people are pulling 10 people, and on the other hand, 11 people are pulling 9 people. So it's easier to pull these 9 people. So you could say, hey, you could also say that there are fewer electrons to be pulled by the nucleus. And that's all. But to be pulled by the nucleus. That's why each successive ionization energy is slightly higher. Generally, it's slightly higher than the other one. So remember, each successive ionization energy is slightly higher. Why? Because each successive electron is removed from a more positively charged ion. And I explained the idea. You have to write this. Each successive electron is removed from a more positively charged ion, because now the remaining electrons would would experience or feel a stronger pull from the nucleus because of the higher charge. And you also realize that the higher positive charge, and you also realize that there are fewer electrons that need to be pulled. But that's what you need to write in the exam, if they ever ask you. Have they ever asked this? No, they haven't. Can they ask this? Yes, they can. And you would also think of it like this, that the net charge, I'm giving you all the concepts in one place. See, if you increase the charge, it's 2 plus, and then it's 3 plus, the 4 plus. This net charge right here, this net charge is preventing the electrons. The net charge of the ion is preventing the electrons from going out. It's preventing you from plucking those electrons. So you could also say, hey, the net charge, the 2 plus, the 3 plus, the 4 plus, the higher the charge, the higher net charge. The 2 plus, 3 plus, 4 plus, the higher net charge of the ion is preventing electron from being plucked, from being removed or plucked. So all of these ideas may be tested in the MCQs. What do you need to write in theory? The pink part. Each successive electron is removed from a more positively charged ion. And now you know the concept behind it, because the more positive charged ion would mean the higher net charge would prevent the electron from going out. It would also mean the stronger hold on the remaining electrons. It would also mean fewer electrons to be pulled by the nucleus. All of these ideas are true. But my question to you guys is, since the nucleus pull is now distributed in less electrons, so it would be absolutely, Zumar, absolutely. My question to you guys is something else. Would there be a big jump? Would this just be slightly higher, or would there be a big jump? Slightly higher or big jump? This general increase is also a proof of subshell. When you talk about successive ionization energy, that's a proof of subshells. But these big jumps are actually proof of principal quantum numbers. So will there be big jumps here? No, because it's the same principal quantum number. But now let's come to the ninth ionization energy. Ninth ionization energy. If I talk about the ninth ionization energy and I compared it to the eighth ionization energy, and the ninth ionization energy, I want to compare the two. See, sodium was 281. I removed this, and now I have to compare the eighth ionization energy. The eighth ionization energy would give me this, right? It would give me 281. This was the first, and if I were to talk about the eighth ionization energy, it's sodium 7 plus gas going into sodium 8 plus gas and removal of the electron, right? Now, and that's the eighth ionization energy. Now I have 281, right? Because realize that all 8 are not removed here. One of those 8 electron is removed here. So if one is removed here, the remaining 7 are removed from this, and you get 2, 1 right here. Now what if I remove the ninth electron? The ninth electron. So it was already 8 plus, and now I'm removing the ninth electron. It is what? 2, which is 2, 1, right? That's the 8th ionization energy, 2, 1. And then when I write the ninth ionization energy, it's 2. So I removed this stuff right here. This was the electron I removed in the ninth ionization energy. That's good stuff. But in the 10th ionization energy, my bad. You guys didn't even correct me. Thank you for correction. In the 10th ionization energy, right here, now I'm removing this electron, the electron in the inner shell. Pehle though I was just removing this one to give you 2. It's the same thing as I wrote above. See, this is like the first electron that I'm removing. Doesn't really matter. It's giving me 2, 8. Doesn't really matter. But now when I remove the second electron, now there's a difference. Because when I remove the first electron, let's suppose I required X amount of energy. But when I'm going to remove the second electron, now I can compare the two. So that was my bad. Not 9th, it will be 10th. My bad, Because realize one thing. See, if I remove this electron right here, ye jo electron hai, I remove this. Good stuff. Good for me. Just like when I was removing the outermost electron. Good stuff. Good for me. I removed it. But now when I removed the other electron, the successive electron, now I can see the difference between this and this. Now I can see that, hey, I'm removing the second electron from a shell closer to the nucleus. Here, this electron right here, I didn't remove it. I just went from this to this. Just like I went from this to this. Yeah, this to this. I want to go from this to this. Yeah, makes sense. So it's be the 10th, not the 7th. Sorry, call. Not the 9th. Sorry. So not the 9th, but it's the 10th, because now that I remove this electron is being removed from a shell closer to the nucleus arena. Again, think about it for a moment. When I removed this electron, it's 2, 1 now. It's 2, 1 now. But when I remove the 9th electron, it's 2. I'm still removing this electron right here. This electron, the outermost, in the second principal quantum number. I haven't removed the electron from here. And you can even visualize this. I first removed this, good stuff, good for me. But when I removed the second electron, now I was able to compare the two. But now, if oh my God. Wait a moment, guys. Wait a moment. Okay. If I remove the 9th electron right here, the 9th electron is still being removed from this stuff. See? If I am removing the 9th electron, it's still being removed from the second shell. The first was removed here, and the rest 8 electrons are going to be removed from this shell right here. So this is the first electron being removed, and all the other 8 electrons are going to be removed from this shell. So I'll even show it to you. That's what I say. See, even I made a mistake. That's crazy. 1, 2, 3, 4, 5, 6, 7, and that's it. So see, this was the first ionization energy, second, third, fourth, fifth, sixth, seventh, eighth, ninth ionization energy. Make sense? I'm removing the ninth electron from the same second shell, ninth ionization energy. And now when I go on to the 10th ionization energy, there's gonna be a big jump. Now you guys see the idea? So it's better to visualize it even for yourself in shells. So first ionization energy, second, third, fourth, there's gonna be a big jump between first and second. And second, third, fourth, fifth, sixth, seventh, eighth, ninth, all the same, all slightly higher. But when I move on to the 10th ionization energy, only then would I see the big jump between the 9th ionization energy and the 10th ionization, because the 10th electron is being removed from a shell closer to the nucleus. Yeah. So it's not a big jump here. This is just a slight increase. My bad. And this one is the big jump. Yeah. I hope I made sense, guys. So between the 9th and the 10th, there will be a big jump. Make sense? Asan? Mushkil? Now it'll make sense. Now it'll make sense. Great. Now I want you guys to do a couple of questions on your own. See, this is like sodium. This is the electronic configuration of sodium. The first is removed very easily. These 8 are removed less easily, and these 2 are very difficult to remove because they are the closest to the nucleus. See, and you can even visualize it here. So first ionization energy, good for me, doesn't tell me anything. But when I remove the second electron right here, that tells me that the first electron was in the outermost shell. And as the first ionization energy, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth. Till the ninth ionization energy, I'm in the second shell now. So the ninth ionization, the second, third, fourth, fifth, sixth, seventh, eighth, ninth, this is in the same shell. But now the 10th ionization energy right here, the 10th ionization energy, that's the real deal. That's the deal breaker. Because now the 10th electron is being removed from a shell closer to the nucleus. The 10th electron is being removed from a shell closer to the nucleus. Yeah? Visualization. What was I saying before? I was saying rubbish. Chemistry ki main chemistry kara raha tha. Okay. Now see, these are a couple of definitions. The first ionization energy of an element is the energy required to remove one electron from a whole mole. It's better to say to remove 1 mole of electron. Instead of saying 1 electron from a whole mole of gaseous atoms, you could say, is the better way of saying it is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to give you 1 mole of positive ions of that element. But don't write this definition, write my definition, please. A couple of questions. My questions. Look at this. If I were to write aluminum, if I were to talk about aluminum, it's 13, right? It has 13 electrons. If I write the electronic configuration for it, it's 2, 8, 3. Right? So if I remove the first 3 electrons, the first ionization energy, the second ionization energy, the third ionization energy, does it matter? Does it matter to me? The first 3 ionization energy, does it matter to me? Should the first 3 ionization energy matter to me? No, it doesn't. It's from the same shell. It's just going to be a slight increase. Why would there be a slight increase? Because each successive electron is being removed from a more positively charged ion. That's it. But if I were to talk about the 4th ionization energy, would there be a big jump between the 3rd and the 4th? Would there be a big jump between the 3rd and the 4th? Manur, I'll cater to your confusion at the end. Would there be a big jump between the 3rd and the 4th? And that's the big jump. See? First it was 580, 1820, 2750, and then 11,600. Which means that the outermost shell had how many electrons? 3 electrons. And how do I explain this? That the 4th electron is removed from a shell closer to the nucleus. Closer to the nucleus. And then you will be removing. So 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th. So how many electrons have I removed? 1, 2, 3, 4, 5, 6, 7, 8. I removed the first 3 from here, and then the other 8 I removed from this shell right here. Right? Now, I removed 8 electrons from this shell. But now when I'm able to remove the 12th electron, the 12th electron is being, it requires 2 lakh kilojoule per mole energy. Remember, ionization energy is kilojoule per mole. So if I removed the the 12th electron is being removed from a shell closer to the nucleus. It's being removed from the innermost shell. That's why it has 2 lakh kilojoule per mole ionization energy. And that's basically that. So the big jumps gives you idea about principal quantum numbers, and the small the slight increase tells you about these subshells. Yeah. And again, this does not apply to D block elements, because D block elements only have 2 electrons in their outer orbit. So you can, D block elements only has 2 electrons in its outer orbit, 4s2 or maximum, it can also be 4s1 for chromium and copper, but it's normally 4s2. So if I'm saying, hey, I removed 2 electrons here and now there's going to be a big jump between the 4s and the 3d, well, that would be true, but it doesn't mean that it's in group 2. It doesn't mean that it's in group 2, or group 1. So I can't use the idea of ionization energy to determine the group number for D block elements. That's the exception that we talked about at the start as well. Yeah, acha. Again, let's come back to Manur's confusion. बस एक ये समझाना. Manur, your confusion. Let's talk about this. This is sodium. Again, let me show you the graphical representation of sodium. Yeah, Manur? So sodium was 281. Always remember, the outermost electron is being removed first. This electron was removed. Does it matter? Do we care, Manur? Do we care that about the first ionization energy? No, we don't. Okay, let's suppose X amount of energy was required to remove it. Awesome, great stuff, awesome, all good, all good. But when I removed the second electron, it required a much higher ionization energy, which means what? That the second electron, this stuff right here, is removed from a shell closer to the nucleus. This is removed from the second principal quantum number 2 right here. It's being removed from this 8, one of these 8. That's this. And this was the first ionization energy. So this is the first, that's the second, that's the third, that's the fourth, that's the fifth, the sixth, the seventh, the 8th, the 9th, and the 10th, and the 11th. Yes, Manur, agreed with me? Now, see, first, the second ionization energy, this is a big jump. Why? Because the second electron is being removed from a shell closer to the nucleus. Now, you remove the second electron right here. तो अब ये कितने हुए? 7. Then remove this. 6, 5, 4, 3, 2, 1, all here. I removed all of the electrons from the 8 principal quantum number 2, which had 8 electrons. See, I removed all 8. Now, after I remove all 8 electrons, Manur, after I remove all 8 electrons, and I move on to removing this electron right here, which ionization energy is this? Removing the electron from the lowest principal quantum number. Which ionization? Well, see, these are already 9 ionization energies. 1 plus 8, 9 ionization energy. 1 plus 8, 9 ionization energy, right? We are at the 9th ionization energy. So if I remove electron from this shell right here, which ionization energy would it be? The 10th ionization energy. So there's going to be a big jump between the 9th ionization energy right here and the 10th ionization energy, not between the 9th and the 8th. Yeah. So a big jump between the first and the second for sodium, and the 9th and the 10th. Why? Because the 10th electron is being removed from a shell closer to the nucleus. And why between first and second? Because the second electron is being removed from a shell closer to. Why is there a slight increase? Because each successive electron is being removed from a more positively charged ion. Make sense, guys? Asan? Yeah. More energy would be required in the 10th ionization energy compared to the second ionization. You see? The 9th is also, ionization energy slightly increases, Manur, so the 9th would be more than the second. But we need to look at the jumps. So first and second has a jump, which means that the outermost electron of sodium is 1. Then these 8 are all in the same shell. And then the 9th and the 10th, there's a huge jump, which means these 2 electrons are the innermost. So how do we write the electronic configuration? It's ulta, 2, 8, 1, because outermost is removed first. 9th is higher, yes. Makes sense now, Manur? Easy peasy lemon squeezy. Guys, Asan, you got it. Thank you, thank you. Noor is saying you make chemistry so easy. I'm glad, Noor. I'm glad, kiddo. I'm actually glad. To talk about a couple of more things. You want me to give you guys a couple of more diagrams, probably? Yes, do you want to look at a couple of more diagrams? This right here, maybe. See, large jumps in ionization energy after the 7th and the 15th ionization energy. The large jumps in ionization indicate a new. See, the large jumps in ionization energy indicate a new electron shell closer to the nucleus. I don't know where I took this snippet from, but I took it anyway. See, this is for sodium. Look at this. The general increase in successive ionization energy is due to the increase in effect. Forget about this for now. It's due to the electrons being removed from a more positively charged ion. And this is a large gap between the first and the second electrons, as the second electron is removed from an energy level closer to the nucleus, or from a shell closer to the nucleus. This large gap between the 9th and the 10th electrons, as 10th electron is being removed from an energy level closer to the nucleus. Yeah. Easy peasy lemon squeezy. Done, sir. Okay, guys. I hope you guys enjoyed. Bye bye. Ciao, ciao. Allah Hafiz. Bye. Bye, guys.